Congratulations on hitting the end of this chapter where we were learning about class templates. And we saw that class templates are a way we have to set up a class blueprint that will be used by the compiler to generate actual class template instances. And we actually saw how this could work using the CPP Insights tool. We can really look at which class template instance was generated as a result of the things we create in our C++ code. We started out by giving you a chance to create your very first class template for the box container, and all we had to do was put in our class template declaration. We also had to put in these little t's to really make it very clear to the compiler that these guys are of a class template here, and the compiler would replace in the actual type for the template argument we pass in when we create an object of box container, for example, that works on integers. When we created an object that would work on doubles, we were able to achieve something like this, and it was really cool. We also saw that template instances are generated once in your code, so the only template instance that is generated is going to be reused by every instance that you create in your code. And we saw that only methods that are used are put in your template instance. Those that are unused are going to only be in as declarations, so definitions are going to be omitted for this. We had a chance to look at this even in CPP Insights. We also had a chance to look at non-type template parameters, and we saw that these were hard-coded types that you could put in your template declaration. And when you hit the point where you want to create an object of this class, you will plug in actual values for this type, and this data will be available for use in your class member functions. We saw that this is really not recommended because it is going to clutter your code. Every member function implementation needs to be decorated with this same template declaration, and this is really bad. It is not worth it. We can mostly achieve the same thing by passing this data as a parameter either in our constructor or on any member function that needs to use this piece of data, so you need to be aware of this. We saw that we could pass default parameters to our class templates. For example, here we could default the type to int and our value to 10, and this would work really well if you need this kind of setup in your code. We saw that we could force the compiler to generate explicit template instantiations, and we saw that the syntax to do that is what you see here. You specify which arguments you want to generate an instance for. And if you do things this way, the compiler is going to put in all the member function implementations, even if many of those methods happen to not be used in your code. So this is something you can do, and it is good to test out your code and really see that the template instances that are generated are what you expect to be generated. Use this if it makes sense in your code. It is going to make your job easier, especially in debugging your template instances. We saw that it is possible to specialize our class template for a given type, and one way to do this is to fully specialize a class template, and the syntax to do that is what you see here. We saw that this was really bad in that it forced you to implement every single method from your class template if you happen to need that method to be available in your template specialization. Another thing is that this was a full class. It is not a class template. So this is going to be subject to ODR violation if you put member function implementations in a header file. We saw that we could avoid this by either marking this little guy as inline or moving this in a CPP file. We moved on and looked at how we could specialize a single method from a class, and again, the syntax to do that is really simple, as we saw in the chapter. Next, we looked at a few lectures to really try and make it easy to implement operators for our class templates. And we saw a case where we could set up function templates as friends to our own class template. And one thing we saw that we really need to do is to mark our friend declaration either with this empty set of angle brackets or the angle brackets with a tn for our template parameter. This would tell the compiler that our friend function is a template, and this would avoid unnecessary linker errors that we would run into otherwise. We saw that another way around this problem was to put the method implementation inside your class and put that in a public section, and this would make this method available, and this would have access to private data in our parameter object here. For example, we had access to the mSize member variable, we had access to the mCapacity member variable, we even had access to the mItems pointer that we can use to access our data using the array access operator that we have here. This would work. We closed the chapter by looking at different ways we can insert compile time checks for our class templates. We saw that we could either do that using type traits and static asserts. We also had a chance to see how we can use concepts to constrain our class template. And the syntax is really simple. All you have to do is add a requires clause to your template declaration here. Of course, there are other syntaxes you can use that we saw in our chapter on C++ 20 concepts, but this is going to work. We also saw that we could put constraints on our methods without putting them on the entire class like we are doing on top here. All these are things you can do. One thing worth reminding you is that we don't have to put in the keys that we put in here previously with newer compilers, and by newer compilers I mean GCC 11, Clang 12, and the latest compiler from Microsoft. If you put this in, you're going to have a bunch of weird compiler errors that we don't really want to deal with. So make sure you put your code exactly like we see it right here. We could also put a bunch of requirements on our methods as we see here. And this is going to work. Here is a simple implementation of a few of the methods. And again, notice that we are repeating the template declaration with our concept constraint, and this is a requirement for this to work on most modern compilers. I think this is a strong requirement for Clang and the compiler from Microsoft, but if you don't put in this requires clause, it may work on the GCC compiler, but I don't really recommend this. We also saw a bunch of built-in concepts. We had a chance to learn about some number concepts, some comparison concepts, and some other concepts that you can play with in your C++ code. Next, we had a chance to look at a few examples. We had a chance to build our own output streamable concept and apply it to our output stream operator to make things work really well. And in closing, we had a chance to build a number concept which would prevent us from treating booleans and characters as numbers and make our function here a little safer to use. This is really all I had to share in this chapter. I hope you found it interesting. We are going to stop here in this chapter. In the next one, we're going to learn about move semantics. Go ahead and finish up here and meet me there.